Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay. The advent of polymerase chain reaction, or PCR, stands as a watershed moment in the history of molecular biology. Kary Mullis' articulation of this technique in 1980, though initially met with skepticism, rapidly transformed fields ranging from medical diagnostics to forensic science and evolutionary biology. This essay undertakes a detailed examination of PCR's foundational principles and purported benefits, aiming to evaluate the claims inherent within Mullis' concept, as elucidated early in its development, by focusing on the original ideas before commercial development and widespread use dramatically influenced its practical application. This study restricts its scope to examining PCR's underlying theoretical foundations, exploring the mechanisms, methodologies, and evidence that underpin its potential and perceived limitations, and examining the initial criticisms and subsequent refinements pertaining to its proposed utility and efficiency. Section 1. Initial conceptualization of strand replication. The initial conceptualization of PCR hinges upon the cyclical repetition of three core processes: denaturation, annealing, and extension. Denaturation, the first step, necessitates heating the double-stranded deoxyribonucleic acid template to disrupt the hydrogen bonds holding complementary strands together, yielding single-stranded deoxyribonucleic acid molecules. Mullis postulated that precise temperature control was paramount, proposing a range sufficient to ensure complete strand separation, yet devoid of excessive heat, which could degrade the deoxyribonucleic acid or the polymerase enzyme. Annealing, the second step, involves lowering the temperature to permit short, single-stranded deoxyribonucleic acid primers, complementary to specific target sequences on the single-stranded deoxyribonucleic acid template, to bind. Mullis emphasized the importance of primer design, stressing the need for sequences unique to the desired target region to minimize off-target amplification. Subsequent extension, the third step, employs the deoxyribonucleic acid polymerase enzyme to extend the annealed primers, using the single-stranded deoxyribonucleic acid as a template, thereby synthesizing new deoxyribonucleic acid strands complementary to the template. Mullis initially utilized the clenofragment of deoxyribonucleic acid polymerase I from Escherichia coli, which was thermally labile, necessitating repeated enzyme additions after each denaturation step. The perceived elegance in this initial design rested on the exponential amplification achieved through iterative cycling, which Mullis believed to unlock previously unforeseen possibilities for deoxyribonucleic acid analysis from limited sample quantities. The conceptual framework rests on the precise control of temperature and the judicious selection of primers, the potential of which warrants further examination. Section 2. Primers and target sequence specificity. The cornerstone of PCR's specificity resides in the design of the deoxyribonucleic acid primers. Mullis contended that primers must exhibit high affinity for their target sequences to ensure efficient annealing and subsequent extension. He advocated for primers of sufficient length, typically around 20 nucleotides, to guarantee uniqueness within the genome and minimize spurious amplification events. Furthermore, Mullis acknowledged the potential formation of primer dimers, resulting from self-complementary regions within or between primers, leading to non-specific amplification. Therefore, he proposed careful consideration of primer sequence composition to mitigate this phenomenon. He also stipulated that careful calculation of melting temperatures for primers was crucial for efficient annealing and amplification. The initial descriptions underscore the importance of primer design and its role in determining the accuracy of the amplified product, yet the practical challenges surrounding complex genomic contexts were initially underestimated. The predictive capability needed refinement to adequately address the complexities of real-world biological samples. The degree of accuracy obtainable with the initial methodology requires further assessment in light of modern understanding of genome complexity. Section 3. Amplification efficiency and limitations. Mullis posited that PCR, in theory, could achieve exponential amplification of the target deoxyribonucleic acid sequence, doubling the amount of deoxyribonucleic acid in each cycle. This exponential growth, he argued, would enable the detection of even minute quantities of deoxyribonucleic acid material. However, he acknowledged several factors could impinge on overall efficiency: incomplete denaturation, suboptimal annealing temperatures, or insufficient extension times could lead to decreased amplification. Furthermore, the depletion of deoxyribonucleotide triphosphates, or DNTPs, and the gradual accumulation of pyrophosphate during the extension phase could inhibit polymerase activity. Mullis proposed that careful optimization of reaction conditions, including reagent concentrations and cycling parameters, could mitigate these limitations. Additionally, he recognized the potential for enzyme inactivation due to thermal denaturation, particularly with a clinofragment. The reliance on repeated enzyme additions introduced a practical constraint, limiting the scalability and automation of the process. While Mullis initially focused on optimizing the cycling parameters and reagent composition, practical challenges in the original procedure existed, and subsequent refinements to the process would be critical for wide application. The initial efficiency calculations were based on simplified theoretical models, the practical application of which warranted further refinement. Section 4. Early detection and visualization strategies. Initial attempts at detecting amplified deoxyribonucleic acid fragments relied primarily on gel electrophoresis. Mullis described separating the amplified products based on size using agarose or polyacrylamide gels, followed by staining with ethidium bromide, a fluorescent dye that intercalates into the deoxyribonucleic acid. Visualizing the deoxyribonucleic acid bands under ultraviolet light allowed for qualitative assessment of amplification success. Validating the presence of the target amplicon, Mullis suggested sudden blotting as a more sensitive and specific detection method. This involves transferring the deoxyribonucleic acid from the gel to a membrane, followed by hybridization with a labeled probe complementary to the target sequence. This hybridization step provides additional confirmation of the amplified product's identity, enhancing detection accuracy. Mullis acknowledged limitations associated with these early detection methods. Gel electrophoresis provides limited quantitative information, and sudden blotting is labor-intensive and time-consuming. These factors spurred the development of more refined detection technologies, like real-time PCR, which enabled quantitative monitoring of amplification in real time. The early approaches, though seminal, underscore the necessity of improved sensitivity and quantification in subsequent iterations of the technique. The transition from qualitative assessment to quantitative analysis constitutes a significant advancement in PCR technology. Section 5. The transition to thermostable polymerases, a pivotal development in PCR history, stemmed from the discovery and utilization of thermostable deoxyribonucleic acid polymerases. Mullis initially used the clinofragment of deoxyribonucleic acid polymerase I, which was inactivated by the high temperatures required for deoxyribonucleic acid denaturation. This constraint necessitated the addition of fresh enzyme after each cycle, increasing labor and cost. The discovery of deoxyribonucleic acid polymerase from Thermus aquaticus, or TAC polymerase, a bacterium thriving in hot springs, revolutionized the process. TAC polymerase exhibited remarkable heat tolerance, retaining activity even at temperatures exceeding 90 degrees Celsius. This allowed for a streamlined procedure, with the enzyme remaining active throughout multiple thermal cycles. Mullis quickly recognized the advantage of TAC polymerase, stating that its integration drastically simplified PCR and improved its efficiency. Its thermal stability eliminated the need for frequent enzyme replenishment. facilitating automation and larger-scale applications. The introduction of Taq polymerase represented a fundamental improvement, catapulting PCR from a laborious laboratory procedure to a widely accessible and versatile technique. The transition to thermostable polymerases alleviated the limitations associated with thermal denaturation, thereby enhancing efficiency. Section 6. Early applications and perceived limitations. Mullis initially envisioned PCR as a tool, with far-reaching applications across diverse scientific disciplines. He proposed its use in amplifying deoxyribonucleic acid from minute biological samples, enabling the analysis of ancient deoxyribonucleic acid, forensic evidence, and pre-implantation genetic diagnosis. Mullis postulated that PCR could also amplify messenger ribonucleic acid, or mRNA, after reverse transcription, enabling the study of gene expression patterns. In early applications, it was considered a potential new tool for cancer research. He was aware of potential limitations. The possibility of false positives due to contamination was a concern, and he advocated for rigorous laboratory practices to minimize extraneous deoxyribonucleic acid introduction into the reaction. He acknowledged the risk of amplifying nonspecific deoxyribonucleic acid fragments, potentially confounding the interpretation of results. The limitations associated with the initial conceptualization prompted the development of strategies designed to enhance specificity and minimize artifactual amplification. The original vision for PCR embraced a diversity of applications, yet the potential limitations spurred innovation and refinement, ultimately enriching its utility. Section 7. Intellectual property and commercialization. The intellectual property surrounding PCR became a complex and contentious issue. Mullis' initial work was conducted at Cetus Corporation, which subsequently patented the technology. The commercialization of PCR was rapid, leading to licensing agreements with numerous companies. The high cost of acquiring PCR licenses limited broader access to the technology. This raised ethical concerns regarding the equitable distribution of benefits derived from scientific innovation. Despite initial skepticism, PCR quickly became a commercially viable technology, attracting venture capital and driving the expansion of the biotechnology industry. The commercial success of PCR underscored the transformative power that basic research could have on society. However, the accessibility of the technology raised complex ethical considerations regarding the balance between profit and progress. The commercialization of PCR necessitated careful stewardship to prevent undue restriction of its application. Section 8. The Nobel Prize and Lasting Impact. In 1993, Kary Mullis was awarded the Nobel Prize in Chemistry for his invention of PCR. This prestigious award acknowledged the profound impact PCR had on biomedical research and its transformative effect on scientific discovery. The Nobel Prize cemented PCR's status as a foundational technology, stimulating continued innovation and refinement. The recognition that Mullis received for his work inspired subsequent generations of scientists to pursue innovative research. The Nobel Prize served as a testament to the power of scientific creativity and its potential to address critical challenges. The Nobel Prize award elevated the prominence of PCR and solidified its lasting impact on scientific progress, confirming its importance in the field. Section 9. Subsequent refinements and innovations. Following Mullis' initial work, numerous refinements and innovations enhanced the capabilities of PCR. These included the development of reverse transcription PCR, or RT-PCR, enabling the amplification of ribonucleic acid, and quantitative PCR, or qPCR, allowing for the real-time monitoring and quantification of deoxyribonucleic acid amplification. Digital PCR, or dPCR, emerged as a highly sensitive and precise method for absolute quantification of deoxyribonucleic acid. These subsequent innovations expanded the scope of PCR and optimized its application across diverse fields. The initial conceptualization of PCR served as a springboard for subsequent innovation, and scientists continually sought to enhance its capabilities and broaden its utility. These advancements reflect the iterative and progressive nature of scientific inquiry, building upon foundational discoveries to address evolving needs and challenges. The evolution of PCR reflects its dynamic and adaptable nature, enabling it to meet the demands of changing scientific landscapes. Section 10 Current and Future Applications. PCR remains an indispensable tool across diverse fields, including molecular biology, genetics, medicine, and forensics. It is employed in diagnostic testing for infectious diseases, genetic screening for inherited disorders, and forensic deoxyribonucleic acid profiling. Emerging applications include personalized medicine, cancer diagnostics, and environmental monitoring. Future innovations may involve the development of point-of-care PCR devices, enabling rapid and accessible diagnostic testing in resource-limited settings. Furthermore, advances in microfluidics and nanotechnology promise to further miniaturize and automate PCR, enhancing its throughput and efficiency. The continued evolution of PCR reflects its versatility and adaptability, positioning it as a key technology for addressing emerging challenges in science and medicine. PCR will continue to evolve and may expand into areas such as space exploration and synthetic biology. In conclusion, the conceptualization of polymerase chain reaction by Kary Mullis marked a paradigm shift in molecular biology. While the initial process possessed limitations, the core principles of denaturation, annealing, and extension, coupled with the revolutionary use of thermostable polymerases, provided a foundation for exponential deoxyribonucleic acid amplification. The subsequent refinements and innovations built upon this foundation have broadened the applicability of PCR across diverse scientific disciplines. Its impact on biomedical research, diagnostics, and forensics is undeniable. Considered through a critical lens, the inherent claims within Mullis' work have largely been validated, albeit with substantial enhancements and modifications driven by ongoing innovation. The legacy of PCR endures not only as a powerful technology, but also as a testament to the transformative potential of scientific creativity and its profound impact on human knowledge and well-being. The initial skepticism surrounding PCR has given way to widespread acceptance and adoption, solidifying its place as a cornerstone of modern scientific research and clinical practice. This enduring legacy underscores the transformative power of scientific innovation and its ability to address critical challenges facing humanity. Word count 2,250.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.